Now we want to talk about the traditional approaches in making inferences using graphs, which are usually composed of extracting some sort of handcrafted features associated with the nodes based on either a heuristic or a domain knowledge, and then utilizing a standard machine learning classifier such as logistic regression or things like that in order to make the inferences. This here is an old example of a social network. This is a network of 15th century Florentine marriages. And the information from this graph can be used in order to indicate or predict the rise of power for the Medici family. As you can tell from this graph, political marriages were a pretty big thing back then. Now the question is, what kind of node features do you think is important in coming to that conclusion? Well, one of the features that come to mind is the node degree, which is one of the early features to use in characterizing a node. This is basically the number of edges adjacent to the node. Note that obviously for directed graphs, you might have different definitions of nodes. Basically, you can count either incoming nodes only, or outgoing nodes, or both of them. Mathematically, for a node U, degree of U is going to be found this way. Where A is the adjacency matrix, and you're basically summing over the row associated with node U. Node centrality is another type of feature that we need to consider. Whereas node degree kind of only measures how many neighbors a node has, when we're talking about node centrality, it's kind of a different approach. There is one popular and important methodology in order to kind of measure the degree of centrality, which is called eigenvector centrality. Eigenvector centrality, or overall trying to measure centrality, has something to do with how important the neighbors of a node are, rather than just how many neighbors a node has. It can be defined as something like this. Now lambda here is a normalization constant. This is the adjacency matrix. And given that you are kind of associating a measure of importance to every node, this is going to be that measure. Now EV and EU are node centrality measure in some sense. Now if you think about it, it is going to be something like lambda E equals adjacency matrix times E. And this is the pretty definition of the eigenvector and eigenvalue. In further analyzing this relationship here, one thing that we should consider is the parent Verbanius theorem. This is a linear algebra theorem with many implications, but the thing that we want to consider here is that any irreducible square matrix has a unique largest real eigenvalue. And that eigenvalue has an eigenvector that can be chosen to have a strictly positive components. So that is something to consider. Now, given that in lambda E equals AE, E is the eigenvector, and based on this theorem, you can have an assumption based on the largest real eigenvalue, lambda. You can choose E to have all strictly positive components that are associated with a degree of centrality. Now, for a second, let's forget about the normalization term lambda and define this iterative relationship like this, where A is the adjacency matrix and E in the beginning, meaning E0, is 1, 1, 1 transposed, or basically a all one column. After one iteration, E1 is going to include what? In a simple undirected graph, E1 will be basically the degree of each node. Now, ET, starting with the aforementioned E0, will basically be the number of length T paths arriving at each one of these nodes. Now, the centrality basically is kind of found by approaching T to infinity, and the values of the centrality of node U would basically indicate the number of infinite length paths arriving in it. Now, this feature gets computed for the Medici family and the Florentine marriages problem, that it becomes very clear that it's a pretty important feature for determining that task, and therefore it's an important feature to consider in general when we're dealing with the graph problems. There are other definitions of centrality, such as betweenness centrality or closeness centrality, that measure how often a node lies on the shortest path between the two other nodes. This is basically betweenness centrality. And closeness centrality measures the average shortest path length between a node and all of the other nodes. So these kinds of measures are all there. In the book, it's mentioned that this reference has a pretty good summary of these methods. Now, if we consider the node centrality feature, these two families, basically Peruzzi and Guadagnini families, are kind of different, are kind of pretty close in terms of that feature. But the thing is, if you look at the clusters of families that are surrounding them, here we have like a more densely connected, tight-knit cluster of families, but here we have more of a star-like connection. Now, what features can kind of provide information on this so as to make the observation of our entity, which is our graph here, as sufficient enough from the statistical standpoint that makes inference feasible and efficient? To do this, there's something called clustering coefficient, which measures basically the proportion of closed triangles in the node's local neighborhood. Basically, these are basically the features that have information on these. Now, the popular local variant, which is a version of a clustering coefficient, is computed like this. Now let's look at this formula and see what it says. If you have a node and you have a couple of neighbors, this basically indicates the number of times you can select two of the incoming nodes for each one of basically two of the neighbors of a node. So let's say we're considering node U. Now on the top, it's basically kind of has something to do with counting triangles. Basically, you are looking at two edges, two nodes that form an edge, that have an edge between them, and they are both neighbors of U. That basically means that this here is going to be a triangle detected. And NU is obviously the neighborhood of a node, meaning that nodes such that this tuple is part of the set of edges. If this value becomes 1, this means that all of the neighbors of node U are actually each other's neighbors as well. And 0 basically indicates a star connection. So one interesting example of this is that when you're looking at a real-world social network example, or other graph examples in biological sciences, is that if you randomly sample edges, the clustering coefficient would be a lot lower than when you have like a real world example of a graph, like a social network, following relationship and things like that. Consider a graph like this. If we consider a certain node in this graph, there is a definition called Egograph, which is defined per node. This definition basically includes the node itself, its neighbors, and all of the connections between the nodes and its neighbors. Instead of counting the triangles, you can count different cycles or different motifs, which are the graphlets within the node's egograph. You can feel that ultimately this definition can be generalized into a graph-level understanding of the density. Now, what happens when the observation of our entities are in fact graphs themselves? For example, they could be molecules, and maybe we want to look at the different data points, meaning different graphs, and say something about their properties. The approaches that have to do with somehow designing features for graphs or designing implicit kernel functions basically fall into the category of the graph kernel methods. The book mentions that these two sources into references also are great surveys basically going over the different types of methodologies in graph kernel methods. Well, the first thing that we discuss is bag of nodes. Obviously, it is the simplest format to approach this problem, which is basically by aggregating the node level information into basically a bag of nodes. For instance, one could compute histograms or other types of summaries, centralities, clustering coefficients, and things as such, and use these measures as an aggregate measure of a group of nodes instead of a single node. The problem with this approach is that this is somehow aggregation of local observations, and it kind of misses a lot of global context. Now let's talk about the Vase-Lemon kernel algorithm that is kind of pretty important both in terms of the intuition that is kind of, for example, lays the foundation for things such as graph neural networks. At the same time, it looks to the iterative neighborhood aggregation idea and is a pretty clear example of that. To start, let's consider basically a graph that is composed of nodes and edges. The idea is that you want to kind of assign a certain type of information or label to each one of these nodes such that not only it includes the information from the node and hopefully its neighbors, that it also tells you something about the structure and things such as isomorphism and things as such. So the algorithm starts with assigning a initial label to each one of those nodes. This initial label is kind of a node level information. Usually it is simply the degree of the node, and this individual information will be used in some sort of a message passing approach in order to kind of pass the information about the structure along to the neighbors, and those neighbors will pass this information along to their neighbors, and after certain number of iterations you have a good idea of what the structure of the graph is. So first you're going to have the label for the 0th iteration, assuming that this is node V. And this is basically the degree of node V. Now here is how the iteration step works. So the node that we were considering is the node V. So you take the neighborhood of V in consideration, and now considering the neighborhoods of V, you have basically double braces here indicating that it is a multiset, meaning that the repetition is allowed, and then you consider the labels from the nodes that are adjacent to V, and you can basically build this multiset, and then you hash this value and you obtain the new value for the ith iteration. So you can see that after k iterations you have processed k hops from each one of the nodes, so you have kind of a degree k level information on a graph and its a structure. So you can see that it kind of leads to having some sort of a measure between the differences, regarding the differences between two graphs. For example, one of the fun applications of this is to approximate graph isomorphism using this algorithm, meaning that if two graphs are isomorphic, you basically want to have the same label set after k rounds of the WL algorithm, which is what we discussed here. And this is used basically a lot.